Hello friends, in this video I'd like to solve the following problem from the Indian Mathematical Olympiad 1989, problem number 4. We want to find all positive integers n, which are not perfect squares, such that n squared is divisible by floor of square root of n, everything cubed. So my hints for this problem. First, notice that every integer n, which is greater than or equal 1, can be written uniquely, in fact, but we need not the uniqueness of this representation. It can be written in the following way: n equals m squared plus r, where m is a positive integer, r is an integer between 0 and 2m inclusive. And also, the second hint, suppose that our divisibility holds, and try to find some constraints for m. So give this problem a try, and I will see you in a minute. Okay, so here comes my solution. So let's write, let n be equal m squared plus something, where what exactly? Where m is a positive integer and r is strictly greater than 0 and less than 2m. Why is this inequality strict? Well, if r would be 0, that would mean that n is a perfect square, and we are dealing only with numbers which are not perfect squares. Okay, and now suppose that square root of n, floor of it, cubed, divides n squared. And now let's express both sides in terms of m and r. What is the square root of n, floor of it? Well, notice that if I have this representation, my number n is strictly between m squared and is less than m plus 1 squared, because m plus 1 squared is m squared plus 2r plus 1, and r is less than 2m plus 1. So my square root and floor, it's just m. So i.e. m cubed divides, and n squared, as we know, is m squared plus r, everything squared. And I will take this condition and I will try to derive something interesting from it. Okay, so m cubed divides m to the 4th power plus 2m squared r plus r squared. If this is true, then that would obviously mean that m cubed must also divide m times m to the 4th power plus 2m squared r plus r squared. There is no equivalence here, there is only implication, but all I want for now is to find as many constraints as possible, as many necessary conditions as possible. So that means that m cubed divides m to the 5th power plus 2m to the 3rd power r plus mr squared. If you look closely, this part is obviously divisible by m cubed, so this implies that m cubed divides mr squared. Okay, but that means after dividing both sides by m squared divides r, and after squaring both, taking square root on both sides, we have the following constraint: m must divide r. It must. But let's go back a few steps. remember that r is between 0, greater than 0, and less than 2m. So in fact, there are only two numbers between 1 and 2m which are divisible by m. M itself and 2m. So since, let's write it in pink maybe. Since 0 is less than r and r is less than or equal to m, it must be the case that either r equals m or r equals 2m. And so that means, okay, that means i.e. our number is either m squared plus m or our number is m squared plus 2 times m. And let's investigate both possibilities. Case number 1, n equals m squared plus m. What happens then? Well, let's go back once again to our condition, namely this condition. I will copy it. And let's put r equals m. So that is equivalent to the following: m cubed plus m squared. Well, this part is obviously divisible by m cubed, so m cubed should divide m squared. In other words, m divides 1. So there is only one possibility. M must be equal 1. M equals 1, i.e. n equals 2. So we have one solution here. Second case, case number 2, n equals m squared plus 2 times m. And what happens now? Well, let's put our numbers. M cubed divides m to the 4th plus 4m cubed plus 4m squared. Again, this part is obviously divisible by m cubed, so it must be the case that m cubed divides 4m squared, so m must divide 4. And we have only 3 possibilities here. That means that m is either 1, 2, or 4, which means that n is either, if m is 1, then n is 3. If m is 2, then n is 2 squared plus 2 times 2 is 8. And if it is 4, we have 16 plus 8, 24. So we have here 4 solutions. And that means that our solutions, so all in all, that means that the floor of square root of n cubed divides n squared in and only if n is either 2, 3, 8, or 24. Obviously, we are not including any squares. And that closes our problem. So yes, so remember that when dealing with floors and square roots, you can express your number as some square plus some type of remainder. And that closes our reasoning. Thank you for watching, and I will see you next time. Goodbye.